In this video, we present an image-based technique for capturing video of human locomotion that can be rendered under both novel viewing and lighting conditions. We capture imagery of a person walking on a slowly rotating treadmill inside a time multiplex lighting apparatus. As the person walks, their appearance is recorded with a vertical array of high-speed cameras, capturing different lighting conditions at approximately 1,000 frames a second. In about 40 seconds, 36 walk cycles are captured at 10-degree increments relative to the cameras. The lighting sequence repeats 30 times per second and includes 26 basis lighting conditions, 3 tracking frames, and 3 matte frames. The complete dataset contains 108 viewpoints of a 7-dimensional dataset spanning time, lighting, viewpoint, and image space. To process the data, we first process the matte images in each lighting sequence into alpha channels. The matte frames result from illuminating retroreflective cloth on the turntable and treadmill and a gray backdrop behind the subject. We compare these frames to clean plate images to derive alpha channels. We then matte the tracking frames onto a black background. This yields a 4D reflectance field movie for each camera, which can be re-illuminated under new lighting conditions. We compute optical flow between viewpoints, both between corresponding frames in consecutive walk cycles and between the 3 vertical camera viewpoints, producing a flowed reflectance field. From the flow fields, we use view morphing to interpolate between viewpoints as the subject animates. For example, if we smoothly morph the view between 2 consecutive walk cycles, we can remove the subject's original left-to-right rotation to render them walking smoothly in a constant direction. To generate viewpoints from anywhere in 3D, we combine view morphing with light field rendering. The original viewpoints form a moderately sampled light field from a 3x36 array of cameras, shown here as a wireframe grid around the subject. Since our views are only moderately sampled, traditional quadrilinear interpolation of the light field produces significant ghosting. Warping the images using optical flow vectors scaled by the light field interpolation coefficients yields a smoother method of generating novel viewpoints. This allows us to render the subject from arbitrary 3D positions in space. We also simulate shadows that a character would cast on the ground under different lighting environments. We pre-compute the percent of light not blocked by the subject with respect to each of the basis lighting conditions, using geometry derived from the subject's silhouettes. This yields a reliable shadow map that can be used to multiply the radiance of the ground plane. With the flowed reflectance field, we can render the subject into virtual or real-world environments. Here we see our subject rendered into an image-based lighting environment using basic geometry to predict the illumination at the subject position and to receive shadows. The second animation shows a second subject rendered into a 3D environment computed with global illumination. The rendered lighting environments used to light the subject are shown in the lower right. The lighting on the subject and the shadows beneath her change accordingly as she moves through the environment. This third animation shows a running subject rendered into another image-based lighting environment. This final animation shows several instances of a running subject in a different environment.